What is up, good people? We are at Chapter 1, Section 1, Day 2 of Functions and Continuity, continuing our conversation, second day of Functions and Continuity. So, let's talk about other things that you can do with functions. What is a one-to-one function? Well, a one-to-one function is a special function that pairs each output with exactly one input. Let's take a look. Here is a function, and it's defined as the name of it is the f function, and it takes as its input variable x. So you read this as f of x, and the rule that helps you calculate what the output would be given any particular input is you take 2 and you multiply it by x, the input, and you add 1. Kind of like this. I didn't have enough space for the work, so you're just seeing the input here and the output here. So if you have an input of 0, that's 2 times 0 plus 1, that's 1. An input of 1, 2 times 1 plus 1 is 3. 2 times 2 plus 1 is 5. And it works also in the negative direction as well. So you can see I've taken all of these, each one of these rows turns into a point, and you connect them all, and you can see that it's a function. I will say that it passes the vertical line test. That's how you know it's a function. Every vertical line intersects this function at most once. So yes, passes the vertical line test. It also passes the horizontal line test. If all horizontal lines intersect a function at most once, then it is one-to-one. And so if you want to know whether or not each output is paired with exactly one input, then you can see with horizontal lines that yes, it is. Like 5 as an output has only one input. It's 2. 3 has only one as an output, has only one input, that's 1. The output of 1 has only one input of 0. There are no repeated outputs. Let's take a look at here and see. Here's a counterexample. So here you've got the function f it reads like this. The f function is f of x is equal to x squared minus 1. And so you can see here that if you take all of these x values and multiply them by themselves and subtract 1, you get all these y values. So for example, 2 times itself twice is 4, minus 1 is 3. 1 times itself twice is 1, minus 1 is 0. 0 times itself minus 1 is negative 1. Negative 1 times itself is positive 1. Remember, negative times a negative is a positive. And when you subtract 1, you get 0. Negative 2 times itself is positive 4, minus 1 is 3. Notice that we've got repeats here. This 3 is, as an output, is repeated twice. The zeros are repeated twice. And if you were to extend the tables further in either directions, you would get more repeated pairs of outputs. So it's a counterexample. It is not one-to-one. It is not a special function that pairs each output with exactly one input. Here you can see each output, like 3, has 2 different inputs. 0 has 2 different inputs. And that graphically you can see that here with horizontal lines. These blue lines intersect more than once. So like I said, 0 is an input, 0 is an output, a y value, that has 2 different x values. This y value here has 2 different x values of 3. This is a value of 3, this is a value of 3. So the y value output of 3 has 2 different inputs. So that's how you can tell that it is not one-to-one. It fails the horizontal line test. Let's take a look here. This is f of x is defined now here in this particular example as x cubed. Take the input and multiply it by itself 3 times. So 2 times itself 3 times is 8. 1 times itself 3 times is 1. 0 times 0 times 0 is 0. Negative 1 times negative 1 times negative 1. If you have 3 negatives, 2 of them will cancel out and you're still left with 1, so this is still negative 1. Negative 2 times itself 3 times. Negative 2 times negative 2 is positive 4 times negative 2 is negative 8. So it does not fall into this repeated output pattern. Each output has exactly one input. Like the number 8 only shows up once in this table and only could ever show up once in this table based on this rule. It doesn't matter what values of x you choose. only one number times itself 3 times is going to give you 8. And that's the value of 2. These output don't get repeated. And so you can see graphically it shows up the horizontal line test. You draw any horizontal lines you want, it'll only intersect the graph once. It passes the horizontal line test, therefore yes, it is a one-to-one function. Just to and I'd like to just refresh what we also talked about last time, the domain and the range. What is the domain of all these numbers, of all these graphs? Well, if you're going to take each and every single one of these points and collect all the x values, you would get all real numbers, especially considering that this red graph actually extends and continues forever. On the table, you could put any number you want here for the x values, and you'd get a y value out. You can take any number you want and make any pair. Any input would produce an output. The range is also all real numbers, because if you know that this line extends forever and you collect all the y values, you get all real numbers. Same thing over here. The domain is all real numbers and the range is all real numbers. However, the domain over here is all real numbers. You can choose any value of x you want and it will produce a y value. However, those y values have a minimum value of -1. The range is all the numbers starting at -1 and getting higher and higher all the way up. Yeah. All right, let's talk. So a one-to-one function is a special kind of function. Here's another special kind of function. It's called a continuous function. A continuous function is a special function whose graph can be drawn without lifting your pencil. When you get to calculus senior year, or in 2 years from now, you will have a much better definition, a much more mathematically precise definition. But for right now, we're going to use kind of like a graphical idea of, like, just imagine you're drawing yourself with a pencil, you're drawing the graph. If you can draw it all without lifting your pencil, then it's continuous. These functions also happen to be, the functions above are continuous too, all of them. You can draw this one without lifting your pencil. You can draw this graph without lifting your pencil. You can draw this graph without lifting your pencil. Those are all continuous. This squiggly curve thing right here, you can draw the whole thing. Even if it continues going up and down, you can draw it just once without lifting your pencil. Same thing with this V right here. Here are some counterexamples, some graphs that you can't draw without lifting your pencil. So here, these are 4 different kinds of breaks. So if it has a break of any kind, then it's not continuous. Here's one break that's called a jump. If you were going to draw this with your pencil, you'd get to here, and then you'd have to lift your pencil up and start drawing over here, and that's called a jump, not continuous. Here's another kind of break that discounts it from being considered continuous. It's called a hole. Basically, this open dot is the idea of you can zoom in as much as you want, but there's one point that's been removed. Here, this closed dot means the function exists here, and it does not, and the open dot means it does not exist here. Although that's the boundary, that's where it starts, and continues from there. Here, just one point has been removed. So really, if you wanted to draw this, you'd have to pick up your pencil and place it down on the other side and continue drawing. That's a hole, and it makes this function not continuous or discontinuous. Here's something called an asymptote. We're going to spend the last third or so of the course really talking about asymptotes and functions that have them. Really fascinating things. But basically, this dotted line means that the dotted line is not part of the graph. The graph is actually these curved parts, but these curves will go higher and higher and higher, and you can get as close to this dotted line as you want by simply going high enough. It's an asymptote, and you can't really draw the whole graph without picking your pencil up at some point and putting it down somewhere else. Asymptote. Here's another hole, but it's also a point up here. It's sort of called a removable discontinuity. Same thing. You can't draw the whole thing. You could try drawing your pencil, drawing the graph with your pencil right here, and then here, and then here. But then at the end of the day, you've lifted up your pencil, so therefore it's not continuous. Just to review, domain and range. Here, if you were going to say, if you knew that this curve kept on going up and down and up and down and up and down, squiggling like that, and in all directions, then you took all those points and you collected all the x values, then they would be all real numbers. Every real number along the x-axis is represented here because it extends on in both sides and indefinitely. So the domain is all real numbers. The collection of all the x values of all these points is all real numbers. The range, however, is the collection of all the y values. And you notice that this graph doesn't get any higher than the value of 2. It doesn't cross the x-axis. So the range, the collection of all the y values is from 0 to 2, including 0, including 2. It goes up as high as 2, but then any higher than that it does not go. It doesn't go any lower than 0. So this is an interval, the interval 0, 2. This is not representing a location on the graph where x is equal to 0 and y is equal to 2. No, this is an interval. It's talking about all the numbers that are in between 0 and 2, including 0 and 2. Domain here. If you knew that this V-shaped graph would extend forever in both directions in this pattern, then you'd be able to collect all the x values and it would be all real numbers. However, the y values are not all real numbers. This graph doesn't actually go below the value of -1. -1 is its minimum value, and so therefore you can say that the collection of all y values, all the output values, the range would be from -1, infinity. So it starts there and goes up as high as you want. Just as a review. Here's another kind of a function. It's called a discrete function. And a discrete function is a special function whose graph is drawn with individual, distinct, and unconnected dots. It's often defined by individual input-output pairings. So there's often no rule that could create this graph. You just have a collection of x, y coordinate points. And so that's what's called discrete. These rules create smooth, continuous curves, or like you could zoom in as much as you want, and you'd never get individual points. This is continuous. And this is not continuous, it's discrete. You might think that's kind of weird or different, but actually it's really worth studying because all computer information is discrete. It's all zeros and ones, bits and pieces of data. If you wanted a counterexample, none of the above functions are discrete. This is not discrete, this is not discrete, none of these are discrete. It's got to be individual points. So, here's a kind of a diagram that talks about the relationship between all these vocabulary. The biggest category is relations, and if you want a special kind of relation, it's a function. If you want a special kind of function, it's a one-to-one function. And also continuous or special kinds of functions, and discrete or the special kind of functions. And there are some functions, there's plenty of functions that are both continuous and one-to-one, so the overlap, there's plenty here. There's also plenty of functions that are both one-to-one and discrete, but you can't be both continuous and discrete at the same time. Reminds me of my days as a high school soccer player. I was the captain of my soccer team. We weren't that great, so it was kind of easy to be captain. I had a whole lot of other captains to choose from. But SCH soccer is way better. If you're on the SCH soccer team, then you get plenty of respect from me. But I had a lot of fun playing, and I love the game. I don't play it much anymore. I do other things. And stay tuned for some of my other things that I did in high school. That's your audio check. All right, set builder notation and interval notation for continuous intervals. Write the domain and the range of the graph in set builder and interval notation. Here's a graph. You can see it does have the arrows. It's going to keep on going. This is a parabola. It'll keep on extending forever in that direction and that direction. The domain is all real numbers, and here's one way you could write it. I know some people who would write like a capital R and then put a second vertical line next to it, and that's one way to write all real numbers. I'm not going to worry about this over here, but if you wanted to do it in interval notation, that means what x values are in the domain, or you can go as far down as negative infinity and as far up as positive infinity. This is not a location on the graph. It is actually an interval. It's talking about all real numbers. It's the same thing as all real numbers, just a different way of expressing it. Range. The least y value for this function is, and I will let you figure out what is underneath the red dot. Figure out what is the lowest y value on the graph for the function. The range is all real numbers greater than or equal to -6. That's how you would say it. And if you wanted to build a set out of it, it would be all y such that y is greater than or equal to -6. The interval would look like this. You start with -6, including -6, and going up to positive infinity as high as you want. Those are all the y values that are as part of this graph. Here's some actual real-life data, and you notice that it's actually discrete. It's the table shows the number of medals in the United States won in 5 Summer Olympics. You can see, let's take this as the input. You give me a year and I'll tell you the number of gold medals. That's our function. So the input is 2016, what's the output? 46. In the year 2012, the output is 46 also. These are discrete points because you can't, they're individually defined points if you were to graph them. There's no way to say what happened in 2014 in the Summer Olympics, or in 2014 and a half, or at 2015 at 0.75. It's not that. You can't do that because they're individual discrete points of data. This is also not one-to-one, so it's discrete, first of all, and separately it's not one-to-one because you can see we've got repeated output over here. The output of 46 does not have only one input, and it's not continuous. If you were to graph it, you would see points, not a curve. Determine continuity from graphs. Examine the functions. Determine whether each function is discrete, continuous, or neither. Then state the domain and range for each function. So, okay, this function right here is continuous because it has a curve with no breaks or discontinuities. You can just draw the whole thing with a pencil, and that's it. Because you can assume that the function continues forever, the domain and range are both all real numbers. This continues, and if you collect all the x values, it's all real numbers. Collect all the y values of all these points, it's all real numbers. I will say it's continuous, yes. It's also not one-to-one. A side note, this is like bonus information that we're reviewing. If you do a horizontal line test right here or so, you'll hit 3 points. That means it's not one-to-one. Next, the function is discontinuous. It's not continuous at all because there are continuous sections, like this is a section that's continuous and this is a section that's continuous, but there is a break at 2, 1. What kind of a break? It's a hole. So you can say it's not discrete. Oh yeah, you can say it's discontinuous. I will also say it's not discrete. This is what discrete looks like here. Because the function is not defined for x equals 2, like right here. If I say, all right, the input's 2, what's the output? You'd be like, I don't know. There's nothing here. There's no value. The domain is all real numbers, all values of x, except x equals 2. X equals 2 is the one number that is not paired with a y value, so it's not in the domain. The function is not defined for y equals 1, so the range is all values of y except for y equals 1. Same thing. What are the collection of all y values? Well, it's all real numbers except the number 1. Like imagine a number line where the number 1 has just been removed. Side note, as a review, this is one-to-one because it passes the horizontal line test. All of the output have exactly one input. Next, function is discrete because it is made up of distinct points that are not connected. Point, discrete. That's actually how computers think. Like, they don't really think any other way. All data is stored in discrete points, and it's incredibly important. And we need to, I think, if you are going to use math in your life, then you're going to overwhelmingly just you'll see it's a world of data, and it's all discrete data. Very important concept. The domain is the collection of all the x values. Look, here's x values -3, -2, -1, 1, 3, and 4. That's a collection of all the x values of these points, and you've listed them here as a set. And the range is -3, -2, 1, 2, 3, 4. There's a collection of all the y values right there. That's the range. Let's see, I wonder, does any of these outputs in the range get repeated? No. So therefore it also passes graphically, it passes the horizontal line test. You can draw horizontal lines and never touch 2 points, only one, at most one. So therefore, yes, it is 1-to-1. And ladies and gentlemen, that's your video. Bring to me your questions. Oh, you have another video to watch after this as well, about the top 6 need-to-know questions for Inspire. Get those calculators out, get them ready, and watch that video. And after you see the second video, then you're done for the day, and I'll see you in class. All right, we're going to spend 2.5 minutes here and now just going through and practicing some calculator work. So pause the video, grab your calculator, come on back. All right, and now that you're back with an Inspire, here we go. This is what the home screen looks like. We're going to go to the graph, the Scratchpad's graph, and you can use the arrows to do it if you want. Press the down arrow and enter. Yesterday, we used the B button. Okay, so it's asking us, what is function 1 going to be? And we're going to press Control and then the divide button. You notice the picture above the divide button is a fraction bar, and that's what we've got. We've got a fraction bar. X in the numerator, and then in the denominator, you can use the arrows to move down. We have Control and then square root. Kind of notice each button has a little blue picture above it, and if you ever want to access that, you press the Control button. So 100 minus x squared. Enter. Let's graph it. See, whoa, check out this curve. Oh, what a funky curve. All right. Now let's do Control T for the table. And you got a whole lot of preset input and output, and you can scroll up and down. But I wonder what would happen if you could, if you needed to know what the input is. Like it's increasing and decreasing by 1 every time. It goes from 0 to 1 to 2 to 3. But what happens if you wanted to go every half? Press Menu, and then you've got some options here. Let's go to the table, the menu for the table, and then you select it with the arrows. You go down. Let's do 5. Edit table settings. Enter. Table start. Right now it's starting at -4, then goes to -3, -2. Let's start it at 0, and let's go up by not 1, but up by 0.5. See what that looks like. Ooh, 0, 0.5, 1, 1.5, 2, 2.53. And now we've got all the input that we want, stepping by 0.5. Let's go Control T to hide that again. And let's take a look at, oh, if you ever need to bring it back up, you can press Tab and use the arrows. All right, we're going to delete the whole thing. I'm just cleaning up the space. And that's how you get back.